This lesson is on exponential growth. So again, before we can continue, there are a few words I do want to talk to you about. So interpolate means you're estimating a value between two known values, and extrapolate means that you're predicting a value by following a pattern beyond known values. Now, both of these words you would have heard in grade 9. It's been a while since you heard them, so I did decide to just throw them in here again as a quick little review. Also, before we start doing some examples and talking about equations, I did want to go over where you would see exponential growth and what types of questions we're going to be talking about. So exponential growth is in a variety of places. It's definitely something that we can relate to the real world. Bank accounts will follow exponential growth, along with even MasterCards and the interest that they accrue. Cells and bacteria are another big one. So we are going to see these types of examples. They are true, and you will be seeing them as you go into your future jobs or future schooling and that type of thing. During this chapter, we will often be writing our own formulas and trying to figure out our own solutions. And so the following formula may be helpful. So what we have here is a formula that says P of n is equal to P naught. So if you haven't taken physics, that P with a little subscript 0 means P naught, times 1 plus r to the exponent n. So here I kind of break down what each of these terms represent. So P of n is our final population, or our final amount. You can use any letter you want here. It doesn't have to be a P. I just chose P for population. P naught, that little 0, is our initial amount. So again, if you're using C of n for your formula, you would be using C naught. I just stuck with P here. R is our growth rate written as a decimal. So for example, if something was growing by 20%, we would do 20 divided by 100, and so we would be plugging in 0.2 for our R. And n is the number of compounding periods. We will go more in depth into this in future chapters. I did just want to use the correct terminology here so that you've seen it before. A compounding period is basically how many times it's going to be doing whatever it's doing. So for example, if something says that it increases by 20% per day, and you want to know how much there is after 3 days, 3 would be our compounding period. So it's however many times it's going to be doing whatever it said it was going to do. And I know that sounds confusing, but obviously we're going to go through an example. Example 1 says, there are 5,000 yeast cells in a culture. The number of cells grows at a rate of 25% per day. Write a function to determine the number of cells after n days. So the first thing that I'm going to do is go ahead and write that formula that we talked about on the previous slide. So P of n is equal to P of O times 1 plus r to the n. Now I can go ahead and plug in all of the information that I know. So the 5,000 yeast cells is my initial amount. And then it says that it's growing at 25% per day, which is going to be my R. And then finally in the question, we're just writing a function and it says n days. So it's not giving us a specific day yet. So if I plug all of these numbers in, I'm going to be left with P of n is equal to 5,000 times 1 plus 25% as a decimal. 25 divided by 100. We know if we want to change a percent to a decimal, we divide by 100. So 0.25 to the power of n. Now I can just simplify this a little bit more, and I can add the 1 and the 0.25 to get 1.25 to the power n. Now if you're wondering why we have a 1 plus r in our equation, and you don't accept the fact that that's just part of the equation, the 1 is actually representing the 100% that you're starting with. So that's representing the initial value. And if you think about, if you're looking at your second line and you think about what's happening, we have the 5,000 times the 1, so that's going to give us our starting 5,000, plus the 5,000 times the 0.25. So it's really saying our initial 5,000 plus the 25% increase. That's where the 1 plus comes into play. The next part of the question says, how many cells will there be 7 days later? So what we're going to do now is take our equation, but instead of n, we get to plug in 7. So P of 7 is equal to 5,000 times 1.25 to the 7. So wherever I see an n in the equation, I'm plugging in 7. 5,000 times 1.25 to the power of 7 on your calculator. Depending, you may be able to just type this all in. You may have to do this part first and then multiply by the 5,000. Either way, you need to be able to get an answer of 23,841 cells. All of the questions in this chapter are going to be similar. They're going to give you a starting value, they're going to give you a growth rate, and they're going to ask you to write a function or determine how many cells or how many something there will be X days later or N days later. They could also give you a final population, so they could give you the answer and ask you to find one of the missing parts of the information. So they could ask you to find the initial. But at this point in your math career, you do know how to rearrange equations. So just make sure that what they're giving you, you're plugging into the proper spot.